Hi, this is problem number 2 for midterm number 2 for Physics 2211. So the problem states that we have a horizontal spring mass system with Ks, the constant, equal to 210 newtons per meter, and the mass of the object is 0.4 kilograms. At t equals 0, the spring compresses 12 centimeters from its relaxed length, and this mass is released from rest. So now we need to draw an energy graph of the spring mass system. So we know that the block is released from rest, which means that it's all potential energy, because potential energy is equal to 1/2 kx squared, and kinetic energy is equal to 1/2 mv squared. And since we don't have any initial velocity, we know that kinetic energy would therefore be equal to 0 initially. So we can draw that with this curve right here, because we know that it's going to be, so this is kinetic energy, because we know that for every oscillation as the mass moves back and forth, the kinetic energy will increase and then decrease, increase and then decrease. And for the same reason, according to the conservation of energy principle, we know that when K is very high, U would be very low, and vice versa. So we know that since the spring or the mass is released from rest, we know that the potential energy would be high. And when you add these both together, you know that the energy of the system, K plus U equals E, would be at the very top of both of these arcs. So that's the energy graph for part A. Now, assuming friction is negligible, what is the speed of the mass when the spring is released and returns to its relaxed length? So we can write some initial conditions, and the initial velocity is equal to 3 meters per second as stated in the problem, and we are looking for the final velocity. So we also know that the spring is initially at 0.12 meters, and the final would be the relaxed length, which is 0 meters. So we can start off from a fundamental principle, delta E equals W plus Q, and we know that delta E would be 0, or sorry, this would both be 0, and delta E would be delta K plus delta U of the spring, which is equal to 0. Now we know that delta K is 1/2 m delta V squared plus 1/2 K delta X, which is equal to 0. Now when we expand these terms, we have this. Now we can use these values that we had and put it into here, so we know that the final position would be equal to 0, and we're looking for this right here, V final. So now we can just simplify, equal to 0, and move some terms around. And we know that these two would be positive, and we can cross out the 1/2. And now we're just going to divide both sides by m. Now, what we can do is just move this over, so add V initial squared to both sides. Now, Now to solve for V final, our last step is just to take the square root. And using the values from up above, what we can find is K is equal to 210, and the initial X position is 0.12 meters divided by 0.4 kilograms, plus V initial, which was 3 meters per second, so 3 squared, and the final answer is equal to 4.07 meters per second when you plug this into the calculator. Now, let's do part C. Now, since friction is not negligible, the block will eventually come to rest. The block will come to rest when the spring is at its relaxed length. Find the change in internal energy of the block, and we know that there's no transfer of energy Q between the system and their surroundings as stated in the problem. So we're going to start from a fundamental principle. So we have delta E is equal to W plus Q, and as per this, delta Q would just be 0. Now we can break down delta E to be delta K plus delta US for the spring plus delta E thermal, which is what we're looking for, is equal to work. So now when we break these terms down further, we have and we can break this down even further by solving for this, which is delta E therm, which is equal to work minus 1/2 m delta V squared plus 1/2 K delta X squared. Now, what we can do is W minus V final squared minus V initial squared plus 1/2 K X final squared minus X initial squared. And this is equal to 0, and this is equal to 0 because it stops at rest, as stated in the problem, because it eventually will come to rest. Now, finally, delta E therm is equal to W plus 1/2 V initial squared, M V initial squared plus 1/2 K X initial squared. And that is the final answer. Thanks for watching.